when we look at this one, the first thing we're going to do is list our possible rational roots. What divides into 16? 1 and 16?
2 and 8.
2 and 8?
4.
And 4 and 4. All right, so when we type our equation into our calculator and we look at our graph, we try to see if anything's happening at any of those points. We verify with the table. So on this one, what actually works?
4 and negative 2.
4 and negative 2. And those are rational roots because they came from our possible rational root list. We already knew they were possible. They actually are. So now we're going to do synthetic division by these two, because how many more are left? If this is 4 and I found 2, there's 2 more.
There will bet there are.
Okay, so let's do synthetic division. It doesn't matter which one you divide by first. You can divide by 4. You can divide by negative 2. So we have 1. What comes next in this?
0.
0, because there's no cube. Negative 14, negative 12, 16. So we're going to bring down the first one. We're going to multiply. And then we add. And then we multiply. And then we add. And then we multiply. And then we add. And then we multiply. And we have no remainder.
We do it again.
So we do it again. But this time we do it with negative 2.
1.
So we're going to bring it down. We're going to multiply. We're going to add. We're going to multiply. We're going to add. We're going to multiply. And we get no remainder.
1x squared.
Okay. Very good. So this is 1x squared plus 2x minus 2.
Now you gotta use your.
And now we have to use quadratic formula. Whenever you have a number, right here with your linear one, you have to use quadratic. So let's come over here and do the quadratic formula. Negative b plus or minus the square root of b squared minus 4 times a times c all over 2 times a. So what does that give us when we simplify it? This becomes the square root of 12. That was a negative 2. There we go. So the square root of 12. What does 12 break up into?
6 and 2.
6 and 2 are 2. Are there any others? 3 and 4. Okay? Of those, we're going to go with 4 and 3 because we can take the square root of 4. And the square root of 4 is 2. So this is 2 plus or minus 2 roots of 3, all divided by 2. What do you notice about that? A 2 will come out of everything. So what it simplifies to is negative 1 plus or minus root 3. So my other 2 are negative 1 plus root 3 and negative 1 minus root 3. Now these are both real. If you look at the graph, it crosses the x-axis 4 times. The number of times it crosses is the number of real roots. These are both real, but they're not rational. What are they? Irrational. Irrational. So, we have 2 types of factoring. The linear factorization comes straight from here. So every time with the linear factorization, x minus 4, x minus negative 2, which makes a positive. And then we have to change the signs here. So it becomes a minus a negative. It's going to make this a positive, and it's going to make that a negative. And then we change the signs here. It's going to make that a positive. It's going to make this a positive.
Did you do x plus 1 positive and then 3 squared and 3 squared?
You can't because these are slightly different. If they were the exact same, we could. All right. Now the next thing we're going to do is talk about that factored over the set of integers. Now, these are not integers. So when I write that line, the rational ones stay the same. That's why when we have rational ones, we don't have 2 different types of factor for them. They're the same. Because the rational factors stay the same. But with our irrational or our imaginary, we have to go back up a step to before we found those. And when we go back up, it gives this was the part that just is integers. So this is x squared plus 2x minus 2. Those are all integers. Now, this is not called linear because is that the first power? No. These are always x to the first, x to the first, x to the first, x to the first. That's why it's linear. Versus the other one is going to have some other powers in it. All right. Is that good for that problem? Okay. So let's take a look at the next one. And I will let you guys vote. Who wants me to erase the whole thing and start over versus who wants me to talk it through? If you'd like me to erase it, raise your hand. If you're okay with me talking it through, raise your hand. All right, the talking it through wins then. All right, so this one, we look at our leading coefficient or our constant, and we list all of our possible rational roots. So everything that can divide into 40. 1 and 42 and 24 and 10, 5 and 8. That's all of them. Then we look at the calculator. Guys, for this class, I'm going to keep those actual roots not too far away from the origin. I'm not testing can you really manipulate your calculator. I'm trying to test do you understand roots, factors, synthetic division, all that stuff. So, if 40 is one of your options, it's probably not going to be one of your answers. I'm going to keep them a little closer to the origin so you don't spend too much time working with the calculator. So when we look at these, our actual roots were 2 and -4. And so those are real rational, and that's where we start. So we have to do synthetic division by one of them, and then take that answer and synthetically divide by the other. Now, when we look at this result here, this x squared plus 0x plus 5, there is no linear term. So you don't have to do quadratic. You can just take the x squared plus 5, set it equal to 0, and solve it. We're taking the square root of a negative right here. The square root of a negative is I. Anytime I have I am now imaginary. If it's imaginary, it's not any of that. Because imaginary is not real. Okay, so that gives us a positive I root 5 and negative I root 5. So for the linear factorization, it's x minus each one of those roots. X minus 2, x minus -4, which makes a plus, x minus I root 5, and x minus negative I, which makes a plus. Now here, factored over the set of integers. These were not integers, so we have to back it up a step. When we back it up a step, it takes us back to here. An x squared plus 5. That's factored completely over the set of integers.
Why is it x squared and not x?
It was 0x, so when it's 0x, you don't have to write the x. So it's 5 plus 0x plus 1x squared. So that's why it's x squared plus 5. Okay, the next one probably was the most interesting one you did, because did you notice that on E, our leading coefficient was not 1? Okay, so I kind of do want to talk us through that little part and show you that little part. Whoops, I got a little happy with the eraser. And then we'll go back. Now, this is just 2. So our numerator is just 1 and 2. But remember, we divide by all the factors of the leading coefficient. So we have to take 1 and 2 and divide it by 1. When we divide it by 1, that just gives us plus or minus 1, plus or minus 2. But then, 2 is also a factor of 4. So now we have to take each one of those and divide it by 2. So when we take 1 and divide it by 2, we get 1/2. Or 0.5. You could write it either way. But when I take 2 and divide it by 2, that's 1. and it's already written, so I don't have to write it again. And then we have to divide everything by 4. So 1 divided by 4 is 1/4.
Why is divided by 4?
And 2, because these 1, 2, and 4, these right here, 1, 2, and 4, are the factors of the leading coefficient.
Cool.
So now we're dividing them all by 4. 1 divided by 4 is 1/4. 2 divided by 4 is 1/2. It's already listed. Now, here was the thing you had to do on your calculator. You had to change your counting number in the table. Can you do that without me telling you what to do? Okay, let's practice again then. Do you have your calculators out? To change the counting number in your table, you have to go to table set, which is the second key, the blue key, and the window. On table set, you have a couple of choices. You can tell it where to start in the table. That's the first thing. Then the second thing is that triangle. That's what you're counting by, delta. That delta means how do you want it to change? We want it to count by, what you do every time is pick your smallest fraction and type it in. Type in 1 divided by 4, 1 divided by 4, and it automatically turns it to a decimal for you. You don't even have to know how to do it. Just type it in.
And then table starts still be.
Okay? And you can have the table start wherever you want to. I usually do kind of close to the origin, so kind of close to 0. You can have it like with -2. You can have it just somewhere close to 0. Okay, so what you're going to notice when you have your counting number set correctly is that it does give you a 0 at 0.5. When you type this equation in and you count by 0.25, you're going to see that at 0.5, the y value is 0. And when you look at the graph, it bounces right there. It's tangent at that point. So when it's tangent, it tells us that it is a double root at 1/2. You could write 0.5. So because it's a double, we have to divide by it twice. 1, 2 times. You have to divide by it twice. Anytime it's tangent, it tells you it's a double root. When you know it's a double root, you divide by that root twice. That gets us down to here. And when we do, this has no x, so we don't have to use quadratic. We just set it equal to 0 and solve. Whoops, too many equal signs there.
So 1/2 is the only one that bounced?
Yep, 1/2 was your only rational root. Out of all of those, out of all 8, positive 1/2 is the only one that works.
Have to divide by.
So you have to divide by it twice. And then when we solve, we get plus or minus root 2. So, and then one more thing I want to go over. When it's a fraction, we talked through this yesterday. Let's talk through it one more time. When it's a fraction, our root is 1/2. We have to undo that. We have to undo the fraction. So the first thing we do is multiply both sides by 2. And we get 2x equals 1. And then we subtract the 1. So 2x minus 1 equals 0. This is my factor. 2x minus 1. And because it's a double, it is squared.
So is it not linear?
This is still linear because this right here is still x to the first. Inside the factor is still x to the first. That was a really good question. All right, and then we do x minus the root 2 and x minus negative root 2, which makes a plus. Now, for the complete factored over the set of integers, we have to go back up a step. But guys, when we go back up a step, do you see that has a GCF?
Yeah.
We have to take it out. This would be more like a bonus right here. So this is what we do when we go back up a step. Okay, so that one was tricky. That little part right there on that problem I think was tricky. All right, and then F was the last one you did. And earlier you had asked about if it has the little inflection. It's a triple root. This one had one. It had an inflection at an x-intercept of 1, 0. So there is a triple at 1. And then you could see -1 and you could see 5. So if we count this one, the first one is 3, and then 4, and then 5. What's the degree of the function? 5. We don't have to do any work. We just looked at our graph and interpreted what it meant.
Sweet.
So we do have to show it's a triple when we write it as a factor.
Now
And
say-
because they're all rational real, that complete linear factorization and factored over the set of integers are the same. You got one answer. Yes, sir.
Say it wasn't like that. You divide by 3 times.
Uh-huh.
Yeah. Okay.
You could do that. Yes. I could give you one that had 2 imaginaries or 2 irrationals at the end.
Good afternoon. Could I please have Julissa to the attendance office for dismissal?
Yes.
Thank you.
All right.